Let's talk about the different types of light. You are probably familiar with visible light and the rainbow. Now, normally, it's arranged this way, red to violet, or red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. Of course, this is only the part of the electromagnetic spectrum that humans can see. There are very many more types of light out there. Here we have the electromagnetic spectrum of visible light that humans can see. Now, on this end you have the red, over here the blue and violet. Notice that this is measured in nanometers or wavelength. So the longer the wavelengths, the redder the color. The shorter it is, the bluer the color, or violet. Now, humans aren't actually very good at seeing violet, so we tend to only see about blue, but it does depend on person to person. Now, red light is low energy, blue violet light is high energy. So this also goes from low energy to high energy. Notice just beyond red is infrared, which we as humans cannot see without technology. Over on the other end, we have ultraviolet, just beyond what humans can see. Now, some animals can see beyond these, but for humans, we just stick with the standard rainbow color Roy G. Biv. Now, visible light that humans can see makes up an extremely tiny portion of the electromagnetic spectrum. Now, the wavelengths of visible light are roughly 0.5 times 10 to the minus 6, or a couple hundred nanometers, so about the size of protozoan that you recall from your biology classes. You may be familiar with infrared light from infrared cameras or heating lamps. Now, this is the heat you can actually feel. You may not be able to see it, but you know it's there because you can, from a distance, feel the heat of something. So anything that's roughly the same temperature as you gives off infrared light. It has to get a lot hotter and therefore a lot more energy to start giving off visible light. If we go down in energy and thus larger wavelengths but higher or lower frequencies, we get wavelengths about the size of a bug, and that is microwave, a technology you guys are all familiar with. I'm sure because you've been microwaving burritos for a while now. Going even lower energy, you end up with radio waves, which can be very large waves, wavelengths of up to 1 kilometer. Notice that the temperature of things emitting these waves is very low. It's not till we get to hotter temperatures that we actually start seeing infrared and visible. If we go even higher energies, we start getting into ultraviolet, which you may be familiar if you've ever been out on a sunny day and got a sunburn. Yet even higher and even smaller wavelengths, we start to get X-rays and then gamma rays, which is the category for all the highest energy photons. So this doesn't actually just end, it keeps going on. Recall that C is equal to lambda F. This means that if we know the frequency of any type of light, we can figure out its wavelength, because the speed of light is the same no matter what type. So yes, radio, even though you hear it over the speakers in your car, the information was brought to your car by light waves. So let's talk a little bit more specifically about some of the types of light out there. How many of you have noticed that on a hot summer day, light can pass through your windshield? Now, the photons pass through the windshield because the windshield is transparent to visible light. Transparency just simply is a measurement of how easily something can pass through it. However, when the photons hit the car seat, they get absorbed. So what happens to all the energy of the photon is it gets absorbed into the material that makes up the car seat or the steering wheel, the dashboard, etc. Adding energy to it heats it up, and this causes it to give off infrared light, which bounces. However, the windshield is opaque to infrared light, so it bounces off kind of like a mirror. Now, as this happens, more light comes in, heats up other parts of the chair, creating more heat, which is just trapped inside. So this is a greenhouse effect, which happens because the glass is opaque, or it blocks everything, so that's a measurement of opacity. how much a material blocks a particular light. Now, car windows are opaque in infrared and in ultraviolet, but luckily for us, glass is transparent in visible light. This is also the same effect that happens in the Earth's atmosphere, which leads to sunlight coming in, being absorbed by the ground, and then re-emitted in infrared, which gets trapped inside our atmosphere. This is known as the greenhouse effect, and this is why greenhouse gases, which are very good at trapping infrared light, thus making it opaque so it can't escape into space, are such a bad thing. Now, a lot of our technology uses opacity and transparency for different effects. One of them that you're familiar with happens to be the microwave. So microwave is going to send a photon towards your food. Now, inside your food, you have water molecules. They happen to be vibrating at the particular resonance that the microwave has the same frequency. This gets the water molecule very excited, so it bounces around a lot and heats itself up. But we build our microwave so that it can't escape. So there is a little grate in the window that is opaque to microwaves, keeping the microwaves from escaping into your kitchen and thus cooking everybody who's sitting around watching their popcorn pop. Here we have a diagram that shows how transparent the Earth's atmosphere is to different wavelengths of light. On this side you have radio being blocked, but as you get to a certain larger radio wavelengths, it goes all the way down to the bottom, so we can put radio telescopes and what have you down on the Earth's surface and still be able to see what's going on in space. As we go towards microwave, though, the water in the Earth's atmosphere absorbs the energy, and we don't see it on the ground. And the same is true for infrared for the most part. Now, visible light, we have a nice little window, which is why our eyes evolved to see this light, and that means we can actually see into space. Now, as we go further on, some of the ultraviolet gets down here, and that's why you have sunburns. Notice that the transparency and opacity is not the same for every wavelength, which is why you can see through a window, but you can't get a sunburn through a window, as ultraviolet light is what causes sunburns. In the X-ray and the gamma ray, our atmosphere protects us from all these high energy and cancer-causing photons. Of course, if we wanted to look into space, we have to actually put some telescopes up in the upper atmosphere or into space itself if we want to actually see those parts of the universe. Here we have some examples of different types of light. So in this column, you see the frequency and the wavelength ranges. So radio waves. We have AM and FM radio, television, all that technology you're used to. Microwaves. So radar, atomic and molecular research, aircraft navigation, microwave ovens, and even some cell phones. In the infrared, now we're talking about millimeter to the edge of visible light. So we have vibrational spectrum, infrared photography, physical therapy. Of course, visible light, which you know goes from red to violet. So we use regular photography, optical microscopy, optical astronomy, basically seeing where you're walking so you don't stumble into things. Now, humans aren't very good at violet light, and just beyond that is what we call ultraviolet. And we use this to sterilize medical equipment, identification of fluorescent minerals. It is also used in types of astronomy. Even higher energy, we end up with X-rays. So we're talking to very small wavelengths. So we use this for medical examinations, bones, teeth, internal organs. We also use it to treat different types of cancer, which is a kind of a two-edged sword because it can cause cancer and it can also fight cancer. So one thing to note is that millimeter wave and X-rays are both used for security purposes nowadays. They look at different aspects. Moving on, we get to gamma rays, which is the highest category of all, and we use this to examine the thick materials for structural flaws, where you couldn't necessarily get into it and see if there's a crack in the foundation. In treatments of types of cancer, we also can use it to radiate food, which makes it last longer on the shelf. There's a lot of high-tech uses for gamma rays, but they all require a high amount of energy, so they tend to be on the forefront of technology. Keep in mind that every type of material, whether it's glass, air, water, is going to be opaque and transparent to different types of light. Obviously, the atmosphere is transparent to visible, but can be opaque to others. Water, that you may be familiar with, is mostly transparent to visible light, but is, as you go deeper into the ocean, more opaque, depending on the color, which is why it's dark on the bottom of the ocean. In conclusion, every material has its own opacity and transparency ranges, and every type of light has its own uses and unique properties.